Okay. It's working. So good afternoon, everybody, and welcome, Lara. Again, it is a pleasure to have you here and for this seminar. A brief introduction to Lara. Lara is a PhD student at Garching. She got her master at the University of Lisbon, Portugal, working on spectral characterization of young brown dwarfs with supervision of Cora Music. And she got a scholarship of 9 months to go to the Institute of Space Science in Barcelona. And afterward, she got a PhD working under the supervision of Giacomo Peccari, and she's now in the third year of a project working on the demographic of protoplanetary disks evolution in young stellar populations. And today her talk will be about probing accretion and stellar properties in the Orion Nebula with VLT shooter. Thanks again, Lara. I'll give you the minutes.
Okay, yeah. Thank you for the nice introduction. So yeah, I'm Lara Piscarreta, and I know by my last name, maybe some of you think that I'm Italian, but I'm actually Portuguese. But it happened a lot, like in the emails, people putting only one R and double T, thinking that I'm Italian. But yeah, so today I will present the work that I developed for the first paper of my PhD. And it's regarding, as Michele said, probing accretion and stellar properties in the Orion Nebula. And for that, we use VLT shooter. So yeah, I will start by a broad context on the topic, and then I will go deeper and deeper into my main research topic. So let us start with this artist impression of like star formation, which I'm sure many of you already saw. So we all know that it all starts with a cold diffuse cloud of gas and dust, which eventually will undergo gravitational collapse, and then it will form several dense cores. And within these dense cores, because the material is in falling and we need the angular momentum to be conserved, basically the material will start to rotate fast and it will flatten into a disk. So then we will have something like this, where in the center we have a forming young star that is surrounded by what we call a circumstellar disk or a protoplanetary disk. And eventually this disk will dissipate and it will give rise to the planetary systems that we observe today. So within this whole process, there's actually a classical evolutionary stages that have been defined through the different shapes, or I should say slopes, of the spectral energy distribution of these objects. So here I will be talking about the evolution of young stellar objects, and there are mainly two different phases. So we have the protostellar phase and we have the pre-main sequence phase. And if we have a look into the first stage of the protostellar phase, we have what we call the class 0. And here are the young accreting protostars. So this stage is where we don't really have still a defined central object. And most of the mass is actually surrounding this potentially central object. So in what we call the envelope. And in this stage, we see like very strong outflows. And basically the SED just looks like an excess in the infrared part of the spectrum. Then if we move a little bit more further in time, we have the class 1 or the evolved accreting protostar. Sorry, because it's cut there. But here we already start to have more well-defined protostar. So most of the mass here is already in the central object. We have a disk that is starting to form, but we still have some envelope around it. And here we start to have the black body coming from the photospheric emission, but we have a huge infrared excess still. Then we enter to what we call the pre-main sequence phase, where we have a well-defined young stellar object in the center, which will be still accreting mass, but most of its mass has been already accreted by now. And we have a well-defined protoplanetary disk around it. And so we have the stellar black body with still an infrared excess, but less. And finally, we have the class 3, or what we call the weak T-Tauri star, where we basically don't have any infrared excess emission coming from the disk, or we have really a very small portion still, and basically the emission comes from the star itself. So today in my talk, I will be focusing on the class 2, or what we call the classical T-Tauri stars. And before I continue, we need actually to update this SED because this has been done some years ago. So we not only have an excess emission coming from the disk, but we also have a UV excess coming from the accretion process. Because as I mentioned, at this point, we still have accretion ongoing, so material from the disk is being accreted onto the host star. So currently, the most accepted paradigm for accretion is what we call the magnetospheric accretion. And this is true for low mass premium sequence stars. So low mass here meaning lower than 1 solar mass, which is the focus of my work. And this process, also coupled with several different mass loss mechanisms, is basically what regulates the evolution of protoplanetary disks. So what this paradigm says is that basically the stellar magnetic field will truncate the disk at a few stellar radii. And within this truncation radius, the magnetic field pressure will exceed that of the gas pressure. So it means that the gas that is in the plane of the disk will basically be funneled along the stellar magnetic field lines into what we call the accretion flows. And here the gas is traveling at nearly free fall velocity, and it's very hot, to like around 1000 Kelvin. So you can imagine that once it reaches the stellar surface, it actually crashes into it, and it creates what we call the accretion shocks. And these regions are extremely important for us because from this we get emission that helps us constrain this entire process. And namely, I'm talking about an excess continuum emission in the UVB part of the spectrum, but also the emission of additional lines that we would expect for non-accreting premium sequence stars. So this is our well-beloved H-alpha, but also other hydrogen recombination lines, such as, for example, Paschen beta and bracket gamma, and also other metallic lines such as helium and calcium are emitted here. So if we go back to the SED that I was showing you, we can update it now with something that I clearly didn't do it in my iPad super quickly. But the idea here is just to show you that we expect an excess emission coming from the disk, but also a UV excess coming from accretion on top of the photospheric emission in the star. And this, of course, will leave an imprint in the spectra of our sources, which I'm showing you here. So just to summarize this figure, which can be a bit confusing. So we have our observed spectra in gray or in black, basically. And this is the addition of two components. So we have the stellar photosphere here in blue, and then we have an additional excess emission, which comes from accretion. And in the community, usually we model this using a set of isothermal hydrogen slab models. So you can see that if we add these two, we get our best fit, which is represented here in red. And this part of the spectrum is particularly important to constrain accretion because we have here this break, which is the Balmer jump. And this is exactly where we can get accretion properties such as accretion luminosity, which then with stellar properties, we can convert into mass accretion rates. But I will talk a little bit more about that later on. So another thing that I want us to focus is on the time scale of this evolutionary stage, which here is more on the short side. So this has been updated a little bit throughout the years. So now I would say that it's generally accepted that the typical disk lifetime in nearby star-forming regions is at the order of a few megayears. So between 2 to 3 megayears, and we know this through this kind of plots. So this is disk frequency as a function of age, and this frequency is basically the ratio of sources that have infrared excess emission to the entire population of sources from a particular star-forming region. So all of these data points are different star-forming regions at different ages. And what we see is this behavior that decreases exponentially. So from this, we can deduct e-folding times, which are typical between 2 to 3 megayears. Now, this disk lifetime is particularly important because it basically sets a time ceiling for the time available for planet formation to occur. So it means that with 2 to 3 megayears, it seems that planet formation needs to occur quite quickly. And if we would have a longer time scale, we would have more time to form our planets, which would translate then into different characteristics for the planetary systems that would come out of that. And so this is why we're particularly interested in trying to constrain this time scale. Now, it is still a timescale that is highly debated in the literature, and there are authors that argue that it is indeed, in fact, a bit longer. So this is a work by Falsner et al. 2022, and in this case, they argue that these shorter timescales are due to observational biases, in the sense that they probe mainly more distant star-forming regions, which have mainly high mass stars. Sorry. So if we focus on nearby star-forming regions and we get more complete into our samples, it seems that the typical disk lifetime that we get is between 5 to 10 megayears. But the point that I want to make here is that I think we agree as a community that we don't expect a significant fraction of protoplanetary disks that are older than 10 megayears old. And more importantly, we really don't expect a very large fraction of accreting pre-main sequence stars at 10 megayears old. So it has been deducted that it should be around 2 to 3% at 10 megayears. And this is exactly where my work comes in, because it seems that several photometric surveys have identified old pre-main sequence stars. Old here, I'm referring older to 10 megayears, that are still undergoing accretion from the disk. And this has been seen both in galactic massive star-forming regions. So here we have the case of NGC 3603, which is interesting because I noticed as there's a poster here of this particular massive star-forming region right out of this seminar room. And this is a work by Giacomo back in 2010. So you can see that all of the sources that are pinpointed in black show an H-alpha excess emission, which is basically a synonym for ongoing accretion. And I know you cannot see very well the isochrons, but here the dashed blue line is the 10 megayear and the red line is the 0H main sequence. So it seems that we still have a significant fraction of sources accreting at these old ages. This has also been observed extragalactically. So this is the case of LH96 in the Large Magellanic Clouds. And similarly to this, the sources here in red have H-alpha excess emission. And you can see that we have a significant portion of them which seem older than 0.7 gigayear. So today, what I'm bringing here is basically the case of the Orion Nebula. I don't think this massive star-forming region needs a whole introduction because I think it is very well known. But just to refresh our minds, it has a mean estimated age around 2.2 megayears, and it is located at 400 parsecs from us. And it seems that it hosts this kind of population. So if we do the color magnitude diagram for the Orion Nebula, and here we constructed it using the broadbands R and I from OmegaCam, all of the sources that you're seeing here have a disk according to Spitzer, meaning that they show infrared excess emission. And the first thing that we can see is that most of the sources have isochronal ages between 1 to 3 megayears, which is what we expect for the Orion Nebula. But then we have a significant population that seems older than 10 megayears and that has infrared excess and H-alpha excess emission. And the H-alpha excess we know because we observed these sources with the H-alpha narrow filter from OmegaCam. So what I did in the first project of my PhD was to try to answer this question. So in the sense of whether the displacement that we see in the CMD is caused by observational uncertainties or intrinsic properties of the sources, or whether we have in fact a real age difference within the Orion Nebula population. And to do this, we actually obtain accretor spectra for 40 objects, which are depicted here with the yellow stars. And you can see that we're probing a large age range so that we could probe both the seemingly old accretors, but also sources that are in the main locus of the population. And in terms of masses, we're basically probing between 0.1 and 0.8 solar masses. And on the right, you can see their location in the Orion Nebula. An important point is that all of the sources are further away than 0.3 parsecs from the main UV source. And the main UV source is located at the core of the Orion Nebula cluster, which is the trapezium cluster, and it's theta 1 REC. And this is important because if we have a nearby massive star, it will basically impact the disk lifetime of nearby protoplanetary disks. So all of these are still somehow irradiated, but not to the point of having a strong observational impact on it. So why accretor? Accretor is great, and this is a bit of a plug-in for accretor. So it covers a wide wavelength range at intermediate resolutions, which is great for our science. So it goes from the UVB all the way down to the near infrared. This is an example of our spectra, which for some of you might be interesting to see. So we have a bunch of accretion lines, which are different accretion tracers. We have the Balmer jump, which I mentioned previously, which will help us constrain the UV excess. And of course, we have a wealth of photospheric features. Two of those are, for example, the titanium oxide bands at 710 nanometers, which are particularly important to spectral characterize M dwarfs. And also the lithium line, which is important to also corroborate the use of our population. And I will touch upon that a little bit later. So the first thing that we needed to do was to simultaneously characterize the photospheric emission coming from the star, along with the accretion property, the accretion contribution, and an accurate determination of extinction. And to do that, we used a multi-component fitting procedure, which is called FRAPE, and I really like this acronym. So it stands for Fitter for Accretion Properties of Theta Stars, and it was developed by a former PhD student at ISO, Rick Klaas, and it stands upon previous work done by his PhD supervisor, Carlo Manara. And the idea here is to basically, in a self-consistent way, get both stellar properties, accretion properties, and extinction estimates. So to model the photospheric emission, we use a set of interpolated class 3 YSO photospheric templates and Y class 3 because we expect them to be non-accreting. So basically, they don't have the accretion contribution. They can very well characterize the photospheric emission. In the case of the accretion contribution, we use a set of isochronal hydrogen slab models, and extinction is just taken as a free parameter in this fitting procedure. So on the right, you have one of our fitting examples, and it is very similar to one of the earlier plots that I showed. So you can see the best fitted photospheric template in green, the slab model in cyan, and if we add those, we get the best fit to the derived observed spectra. So with this, we can get spectral types, stellar luminosities, also accretion properties as the accretion luminosity and mass accretion rates, and extinction. And let's start by focusing on the stellar properties. So if you're an astronomer and you have stellar luminosity and effective temperatures, what you do is an HR diagram. And the first thing that we see here is that it seems that most of our sources are in fact younger to what it seems in the color magnitude diagram. So they are mostly younger than 5 mega years old. There's still a huge spread, which is something that is very debated in the literature, because it might mean that we have a complex star-forming history, but also other things like accretion variability and etc. But then the interesting thing is that even when we account for extinction and accretion, we still have 3 outliers in the sense that they seem to stay generally older. And these 3 are particularly interesting because at the moment we cannot really conclude anything yet because we lack data to do so. But there are 2 hypotheses to explain them. The first one being that we might just be underestimating the stellar luminosity. So you can think of it as a geometrical effect. So if we're observing a disk that is mostly edge-on, the emission coming from the star will basically be lower than if the disk was face-on to us. So this might just mean that these sources have a higher inclination than all the others. Another thing is that they might indeed be old accretors. And in this case, it would mean that the disk would have been somehow replenished of material so that they can still sustain accretion at these older ages. And one thing that has been coming up in the literature a lot is what we call late stage infall. So it's the idea that in a massive star-forming region, a young one, we still have some nebulosities and clouds that can kind of produce what we call streamers that will in fact replenish the disk and somehow sustain the accretion at these older ages. But unfortunately, only with the excretor data, we cannot get more information on that. And also with archival data, we're missing, for example, ALMA observations, which could tell us something about inclination, or even the SED itself. We don't have measurements at longer wavelengths, which could help us distinguish between edge-on or face-on. Another way that we can further corroborate the truth of our observation is going to lithium, as I've mentioned previously. So lithium is interesting in the sense that it is an ephemeral element in the photosphere of premium sequence stars. And basically, it is depleted with time, so we can use it as kind of an age probe. So we would expect young sources to have abundance in lithium in their photospheres. And what we see is that we detect lithium in all of our sources except for 2. And these 2, this one particularly, it's interesting because we don't see any photospheric features. So it is completely dominated by accretion. So it seems that it is one of the highest accretors in our sample. And in fact, we cannot even run frappe on it because if we don't have photospheric features, we cannot characterize the photosphere. For this one, unfortunately, the signal-to-noise ratio is quite low, so it doesn't mean that we don't detect lithium in these 2. It doesn't mean that these 2 doesn't have lithium. It's just that we don't detect them. So a further thing that we did was to compute the equivalent width of the lithium line, and to do so, we need to take into consideration that we have accretion. And accretion will actually veil the photospheric absorption features. So veiling here means that we just have an excess continuum emission, which basically will make the photospheric lines appear shallower and narrower to what we would expect for non-accreting premium sequence stars. So we can correct this by basically subtracting from our derived observed spectra the slab model, and then we can compute the equivalent width. So once we do that, we get this plot, which is these values as a function of effective temperature. And here I'm just comparing with measurements performed also in extruded spectra, but in the lupus sample. And this is because lupus should have a similar age, estimated age as the Orion Nebula, which is between 1 to 3 megayears. And so what we want to see is just that the mean and spread, so the distribution of the equivalent lithium measurements are similar. And this is because significant lithium depletion seems to only occur after 20 megayears, between 20 and 200. So at these very young ages, we don't expect significant depletion to the point of having accurate individual estimates for ages at this point. But we see that they are in agreement, which further corroborates the use of our sources. And also just to compare it further with the literature, there has been this works done by Pal et al. In 2005 and 7, also in the Orion Nebula cluster, which also reported similar equivalent widths for the sources. So now we will have a look into the accretion parameters. And I will just do a brief parenthesis in the sense of having a small introduction for this part here, because I think it's important to mention that accretor has been a very a power force in terms of surveys in star-forming regions to get accretion properties. So it has been used in, for example, Lupus, Chameleon-1, also Upper Scorpius. And one of the main things that we have learned from these surveys is the establishment of the correlation between mass accretion rate and stellar mass. So we expect it to correlate positively, although you can see that we have a huge spread, which is still very debated, but it's thought to be physical and not due to observational uncertainties. And the typically reported slope is between 1.6 and 2. Whereas the spread is between 1 to 2 decks, more or less, so it's huge. But an important point that I want to make here is that most of these accretor surveys have been performed in nearby low-density star-forming regions, such as, for example, Taurus here. And in these regions, we can basically assume that the protoplanetary disks evolve in isolation. So there's no kind of interaction with the environment, or for example, with even stars, so for example, flybys, etc. And it's great to do these first steps into characterizing accretion as a function of stellar properties and also as a function of disk properties. But it is extremely important to go one step further and try to characterize this into more representative star-forming regions, such as the Orion Nebula, and also in the future, hopefully, in massive star-forming regions, such as the Western one. And this is because we know that most stars are formed in these clustered environments, so in massive star-forming regions, and there's actually evidence that even the solar system might have formed into an environment that is similar to the extended part of the Orion Nebula cluster. So we need these kind of statistical surveys also to get these kind of studies into more representative environments. So this was also one of the main points of our work. So if we go back to these plots here, so this is the same that I was showing you, but we also have a correlation between accretion luminosity as a function of stellar luminosity. And this is all the measurements performed in the literature. And then if we add the Orion Nebula, this is what we see. So this is interesting because it seems that despite the higher stellar density and also the higher radiation coming from nearby OB stars, it seems that our measurements populate the same perimeter space in both of these plots. And this is the first time that such measurements has been performed into more distant and more representative environments. Another thing that I want to point out is in this plot right here, which shows that it seems that for each bin of stellar luminosity, our seemingly old sources, which have these circular shapes, are among the ones that show higher accretion luminosity. And this might help us in trying to answer the last and final question, which is if we basically consider extinction and accretion, and most of the sources are indeed younger, then what is mimicking bluer optical colors in the color magnitude diagram? So what is messing with our photometry, basically? And to do this, we tried to isolate the accretion contribution. So the first step was to perform a synthetic photometry on the derived accretor spectra. So we basically convolved the broad R and I filters from Omega Cam with the accretor spectra, and we got magnitudes from that we can put in the color magnitude diagram. And then we basically took advantage of the HR diagram, which translates the pure photospheric magnitudes or measurements And this is because we use the set of isochrons from pizza, for which we have theoretical values of R and I. So we can perform an interpolation using a two-dimensional Gaussian kernel, and we can estimate the magnitudes for the pure photosphere. And once we do this and we put in this CMD, this is basically what we see. So it seems that, first of all, accretion has a significant impact in the photometry of these sources. It seems that once we correct, so this is the stars to these X symbols, it seems that it makes our sources appear fainter and also redder, which makes sense because we know that accretion basically adds an excess continuum in the blue part of the spectra. And also, it seems that most of the contribution, let's say it, is more regarding the color than regarding the R magnitude. Now, this is still work in progress, so I'm happy to discuss this further. We, of course, want to try to have a look into the impact of accretion into different filters. And we aim to do that with, for example, HSC, but also Gaia. And this was just a proof of concept in the sense of trying to understand that accretion can affect the photometry, and so we need to take this into account. And with that, I don't know if I'm too quick because I'm getting to my summary, but so I will just go through them quickly. So what we saw is that once extinction and accretion are taken into account, most of the sources are in agreement with younger ages. However, we have still 3 sources that apparently remain older, and for that we need more observations and further analysis to really confirm their true nature. Then we saw that accretion properties of the Orion Nebula are consistent with those that we observe in lower density star-forming regions, despite the higher star density, but also the higher irradiation environment. And it seems that the continuum excess emission coming from the accretion process significantly impacts the photometry of prime and sequence stars. And here on the right, I leave you the QR code for my paper if you want to have a deeper look. It was accepted not so long ago, about like 1.5 months, so I'm proud of it. And I will just finish with this summary about future perspectives. So as I've mentioned, we want to further characterize the impact of accretion in different photometric filters. And this is very important in, for example, when we move to further star-forming regions where spectroscopy basically is not available. Thank you. So yeah, for example, if we go to the Magellan Clouds or other massive star-forming regions, if we can get a way to have an idea of how accretion can impact these filters, then it's very powerful. And another thing is also that we need these homogeneous population studies of accretion across different ages and environments. And this is crucial to constrain better disk evolution and also to inform better disk evolutionary models. And right now we're actually working on a big population of more than 70 disks in the entire Orion A cloud. And this is nice because it is probing both the region that is still highly irradiated close to the Orion Nebula cluster, but also the more quiescent regions, which are the L1641 and L1647 in the southern part of the Orion A cloud. And with that, I think I finished my presentation, and of course, I'm open to any questions that you might have. Thank you.
So thank you, Lara. Questions? I have a very nice question. Yes. One of the first slides in which you showed the way in which the material is followed.
Yes.
I was trying to figure out how this can happen, but you said that it's more than 10, yes, more than 10,000 Kelvin. So the material is ionized.
Exactly.
So it should follow the magnitudes.
Yeah.
But how can it be that the accretion goes in both directions?
Yeah, that's a good point, actually. Yeah, yeah. It should go, you mean like just because of the positive and negative pole? Yeah,
Okay.
exactly. Yeah. Yeah. I guess it's the diagram itself. Yeah, yeah. Yeah, but basically, like just because the gas follows the magnetic field lines, it creates kind of these accretion flows throughout the different, so throughout the surface of the star, and then it will clash and go into the accretion shocks. Yeah.
And that's it. Now, my question is if up to now it is not possible to have an extinction map of the Orion region.
Yeah, I think there is. Actually, I think there is some extinction maps for Orion. We didn't double check with our extinction measurements yet. Yeah. So yeah, because this is a tricky question in the sense that there's some degeneracy between the extinction and the accretion. So FRAPE, this multi-component fitting procedure, is actually the best way that we have to constrain that up until now. Because it takes everything into consideration simultaneously. And there's another test that we can do, which is we can use the emission lines that come from accretion, and we can measure the line luminosity. And there are some relationships for which we can derive the accretion luminosity coming from that. So if we get the accretion luminosity for different lines, which are at different wavelengths, and we see a dependence with wavelength, then it means that our extinction estimates are not correct. Okay. We've done that, and it seems that there's no dependence, which makes us a bit more certain that we have an okay estimate. But yeah, I agree that it would be a nice look to check the maps of extinction. Yes.
So you said you may lose light from the star systems. So it's a sort of internal extinction, right? It's an additional extinction.
Exactly. Yes.
But it also affects the colors.
Exactly.
Right? So
Exactly.
it moves. It's really.
Yes. Yeah.
But you have high resolution spectra. I call this.
Yes.
It depends what you're doing.
Yeah.
But so maybe you already say that, but I missed it. How do you infer? You are able to infer this extinction? Because, for example, you have if you use interstellar bands, I don't know if you use that or other methods to infer that extinction.
Yeah, we don't disentangle the interstellar medium extinction from the extinction coming from the disk. The only thing that we do is use it as a free parameter here, in the sense that it uses to balance the accretion as well. So FRAPE tries to check what is the best feeding procedure by de-reddening the observed spectra into a grid of extinctions, and then trying to iterate between different combinations of different templates for the photosphere and different slab models.
So you don't use, like, for example, supernovae, we use a sodium. We see absorption of sodium.
Okay, yeah.
Which is, it doesn't tell you anything about the task. It says about the gas. But we found it's a good probe to infer the internal extinction.
Okay.
I don't know if you use these.
We don't, but we
In
could,
general,
because
we call them diffuse interstellar bands.
yeah.
Sodium is one of these.
So sodium, for example, is in the J band. So you mean the doublets in sodium, or?
The line is slightly below 6,000 ohms.
Oh, okay. Yeah. Yeah, in principle, we could use it to say something, but at this point, we didn't do it yet.
Because most of the times we cannot say anything because we don't have spectra with this resolution. And where we have it, we can, in general, principle, we compare the sodium from the host, the sodium from the Milky Way,
Okay.
and we find that the sodium from the Milky Way more or less is correctly estimates the extinction from the Milky Way.
Okay.
That's why we use the sodium.
So you mean the sodium would give us the information regarding the extinction within the line of sight, right? Yeah. Okay. Yeah.
So in that sense, it could be something. I don't know how much you can distinguish between sodium from the Milky Way and sodium from the, since we don't have redshifts.
Yeah.
But with that should in the V's part N, which is the highest, yes, the highest resolution.
Sorry.
This part is 9,000.
Yes, yeah, exactly. So it's still quite high, yes. Yeah.
Yes, probably this is because I did not follow the first part of your nice presentation. At some point, you mentioned the planet formation, the time window, and so on. So my question is, do these studies provide insights not only on how and when planets can form, but also if they actually can form? If these studies can analyze conditions which actually prevent planet formation?
I think so, yeah. So yeah, this is a very hot topic.
Okay.
So no, I think it's okay. So I can say what I know. No, it's okay. It's a very important question. So okay, maybe I can go actually to this slide here. So yeah, for that, like ALMA has been the main like thing about like studying planet forming disks. And what we see is that most of the disks have some kind of substructures, have gaps, have rings, everything. And so we think that within these gaps, planet formation might occur. So basically, it's a planetesimal that is forming and basically creates this gap. But there are other hypotheses as well. And the truth is, there's only one system, which is PDS 70, for which we actually observed protoplanets, and we haven't observed yet anywhere else. So this is like a huge question in the community. What is missing? Exactly. Yeah. Is it regarding in terms of like sensitivity, or like we need better facilities, better interferometric facilities, or is it that somehow we're not detecting the planets that we would expect there? But it's interesting because this observed both in class 2, but also in earlier evolutionary stages, so class 1s. So there are in the literature groups that argue that actually planet formation can start much earlier than what we thought. Yeah, but it's still something that we definitely need to work more on. Yeah.
I have a curiosity.
Yeah.
In the slide you showed before, and you use it. So the extinction law is just it's fixed.
Yeah,
You
it's the
don't change
Cartelli extinction law. Yes.
There are multiple.
There are multiples.
And
Yes.
so that can impact the result.
Yeah. So.
Did you try that when it's something that you or you don't want to?
So the Cartelli extinction law is the one that is implemented in FRAPE, which is the component fitting procedure that I'm using. But one thing that I've tried is, for example, the RV parameter, which also is debated, and especially in Orion. So usually in the ultrasonic medium.
Such a different environment.
Yeah, exactly. So we use the typical 3.1 value. There are people that might argue that it's a bit low and maybe we should use 5.5. We did tests, and it seems that all the both the stellar and accretion properties that we estimate, if we use 5.5, it's not statistically different to what we get for 3.1. And the way that we argue it is that we expect this RV of 5.5 to be within the core of the Orion Nebula cluster, which is not a region that we are probing. So we expect the extinction there to be much stronger. So we are probing the extended part, and that's why we call the Orion Nebula, because it's not really in the trapezium core, which is where we expect this higher value. So yeah, for now we're using Cartelli law with RV equal to 3.1.
Very nice question. I suppose the disks must be different from one star to the other.
Yeah.
Is there any mass dependence on the disk properties?
Yeah.
So is there another 3 parameter?
You mean the disk properties?
Yes.
Not yet, but it's something to. Yeah, we don't really derive any disk properties.
But they will have impact on results or not?
I think so. Let me. This is a very nice question because maybe I can go here. Yeah. So. Yeah. Now, with FRAPE, basically we're using the UVB and visible part of the excretor spectra. But then we have the near-infrared part, which could help us in constraining a little bit more about these properties. It's not something that is in FRAPPE, but it's something that in the future might be interesting. There are some works from groups from Catherine Espayat, for example. I don't know if someone knows, but her PhD student, Kaylee Pittman, actually is using a model where they consider different density accretion flows, but also different excesses to basically try to fit the near-infrared part and to translate basically disk properties. So it's a bit, yeah. So in terms of physics, it's, I would say, maybe a bit more accurate, but with this, it has been shown also because previous works before us already used these simple slab hydrogen models. It seems that we can reproduce well the accretion properties. So it's nice because it's computationally less expensive. And I mean, it's a good first approximation, but for sure it would be interesting to include this part, yeah. And just for curiosity, there's actually, so we expect the disk mass to scale with stellar mass. And this is also why the mass accretion rate scales with stellar mass. So a massive star has a more massive disk, which in turn will translate it to higher mass accretion rates. Yeah.
Ask a question. One of the modelization of the accretion on protostar is quite complicated due to the large number of parameters. One of the most important uncertainties related on what is the process that governs. It's called accretion, photoaccretion, and so on. From this kind of analysis, you can retrieve information about the mechanism of the problem.
Not that I know of. Yeah. So what we consider is just a magnetospheric accretion, where we have the accretion flows, we get this emission, and we basically constrain the accretion properties coming from this excess emission. Yeah. But it's a good thing to look at.
Okay, there are no more questions. Let's thank you again.
Thank you.
The next stop will be next Thursday. Giorgio Valery, and I. No, 2 weeks. Okay, 2 weeks. Sorry. So we don't know. Does anybody know? Leonardo, you know what we will talk about?
Transits.
Okay. So.
Yeah.
So, next slide.
Thank you.
The widest passive